All right, welcome back. We're going to do sections 2.5 and 2.6 today. So let's dive into it. 2.5 is on transformations of functions. So the first thing that we'd want to look at are the graphs of some basic functions. So we might see something like, say, f of x equals x squared. That more or less looks like this, some sort of parabolic arc, right? If I have f of x equals x to the third, right? It looks like this, more or less. My graphs are not great. I'm on this little pad thing, but doing the best I can here. Let's look at, say, f of x equals the square root of x. That is kind of like that. Goes on forever. So these are some functions that you should be aware of their general form, what they look like, right? Some of the polynomials, before we get too crazy with them, x to the fourth looks like this. It almost looks like x to the square, but it kind of gets a, oh, that's not great. It's a little bit more of a round bottom. Ugh, that's not great either, but that's not too bad. And then, what else should we know? The 1 over x, you should probably know that one. Let's say we've got f of x equals 1 over x. That's going to come along kind of the upper right quadrant like this. And then it kind of goes up, and then it has this asymptote where there's no value at 0, because if the denominator is 0, it doesn't exist there. And then it comes back up from the bottom and kind of does that. Right? So more or less, let me just still this picture. It probably looks better anyway. That, right? That's what I was trying to go for. So the absolute value of x, you'll want to know that guy. That looks like this. The absolute value of x. If x is positive, it's just basically x. So that's just that straight line like this. Straighter than that, but straight. And then if it's on the other side, it just returns the opposite. So it's, essentially that. So it creates that V. More like, well, better. I don't know. I don't know why I try. I can't draw. I like to blame it on this little tablet, but I just suck. But there we go. That. I'll get this thing out of my way. Okay. So these are a couple of functions that you want to be familiar with. If I start messing with these just a little bit, let me just scooch this up. If I have f of x equals x squared plus 3, right? Well, for every x value that I plug in there, I'm going to square it just like I did with f of x equals x squared, but then I'm going to add 3 to it, so my y values just all pop up by 3. So I should be able to simply graph this. I'm going to grab a picture of a graph. That one's all right. Let me still it. Yeah, perfect. I like that one. So if I drew x squared, right? And if I wanted to draw it with any level of accuracy, I'd plot a few points first and then try to hit those. But it should go something like this. Not the best curve there, but that's even worse. There we go. That's not too bad. X squared looks like that-ish. X squared plus 3 is just taking all of these values and moving them up by 3. So instead of being at 0, I'm going to be at 3. Instead of being at 1, I'm going to be at 4. So that's all I've really done is taken that parabola and just shifted it up 3. And that's the transformations that we're talking about here, is just taking something that we know and just moving it somewhere else. So that's what we've done here. So for example, if I take f of x equals the square root of x minus 4, right? I should be able to plot this knowing that the square root of x, I'll do in red, should look something like this. Right? That's the square root. It starts at 0 and goes on forever to the right. But that minus 4 says take the square root of x and then subtract 4. So all of those y values move down by 4. For example, f of 0 up here is the square root of 0, but then minus 4. Square root of 0 is 0, so this is just negative 4. So it moves it down here. Right? But everything's going to get moved down 4. This entire graph, every single one of these values gets moved down by 4. And so my graph then should look like this. I've just moved it all down 4, right? So that is called a, oops, my thing, that is called a vertical transformation. So we'll say this, the vertical transformation of f of x is that function, whatever that function plus some c value. I don't know what the c value is. In the first one, it's 3. In the second one, the square root function, that's minus 4. But this f of x plus c gets shifted vertically c units. Right? If c is positive, it goes up. If c is negative, it goes down. Right? Okay. So let's look at, oops, wrong thing. Let's look at this. I want to graph f of x equals, let's say, let's do the absolute value of x and then minus 1. Right? Well, I should know that the absolute value of x, which I'll do in red, the absolute value of x is just this straight line up this way. Oof, that's not a great straight line. Boy, who'd have thought doing a straight line would be a hard thing? But this thing is all magnet, so I think when I touch it, it goes out of whack when I try to draw straight. So I'm just going to go with that theory and blame it on that. Okay. Pretend that's a straight line. The other one's just going to go off in this direction. Yoink. Oh, that was easier. I don't know why the other one was hard, but that's the square root of x. And then if I want to draw the function that I've listed here, I'm sorry, the square, it's the absolute value of x. And if I want to draw the function, the absolute value of x minus 1, that just shifts everything down. And so then my new graph is here, almost an equally wavy line. And there, oh, wow. Well, these are terrible, right? I don't know what else to do other than just not suck, but I can't do that. So there we go, whatever. So that's what it is. It's the V that it just gets, everything just gets pushed down just a little bit, right? Okay. That is a vertical transformation, right? So you can do this with a graph that you don't even know what the function is, right? So if I have, let me just clear this out. We might have something that says the graph of f of x is shown below. Graph f of x, I don't know, plus 3. So if I have a graph, let's just say whatever this graph looks like, let's just do it in red. Whatever this, oh, that's ugly. Whatever this thing looks like, it doesn't matter. The graph of f of x plus 3 is just that thing moved up 3 units. So I don't know why I just made life hard for me, but 1, 2, 3. Oi, 1, 2, 3. Maybe I should just copy it and paste it. 1, 2, 3. But yeah, it should look like, well, I'm terrible with this pen, but it should look like that. Everything's just moved up 3 units, right? Don't test it everywhere because I didn't do a great job drawing this, but that's the idea, right? Everything just boop, 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 up 3, right? All right. My drawings make me sad. Horizontal ones are a little bit different. So we'll talk about how those look before we graph them. But the, let's say a horizontal of the graph f of x denoted f of x minus c, right? So that x minus c is in parentheses with that x, is a horizontal shift of c units, right? Now you notice that there's an x minus c here, whereas in the vertical, did I erase that? I sure did. In the vertical shift, it's that f of x plus c, and you move up or down based on c, but here it's x minus c. So you're going to move to the right if you have x minus some number, but if you have x plus some number, you're going to move to the left. So it kind of goes opposite the sign when you're doing a horizontal shift. So for example, let's say I have f of x equals the square root of x. Right? And again, we know what that looks like. If I can draw it, who knows? It's been a hit and miss day already. Looks more or less like that, right? And so if I consider the graph f of x equals the square root of x minus 3, right? So here it's minus 3, so c is equal to 3, which means there should be a shift to the right by 3. And if I test my domain just to see, I have to have x minus 3 is greater than or equal to 0. Otherwise, I'm taking the square root of a negative number. That doesn't give me a real number. And so if I add 3 to both sides, definitely x has to be greater than or equal to 3. Well, that's not a surprise because c is 3. So this thing isn't even defined to the left of 3. But if x is 3, if I say what is f of 3 in this function, that is 3 minus 3, which is the square root of 0, which is 0. So when x is 3, I have my 0. And so you can bit by bit plug in numbers, but you can see all of these numbers are just going to be shifted to the right by 3. And so my graph then gets shifted to the right by 3. And that's a horizontal shift, right? We can see that in play with a couple of different ones. Let's look at, let's say I have f of x equals x plus 2 squared, right? So in this case, my c, my original function, right, if you want to call it the parent function, is x squared, right? And c is negative 2, right? Because this is x plus 2, so if it's x minus c, then c has to be negative 2, so x minus negative 2 gives you x plus 2. So this is to say that I have a shift to the left by 2 units, right? So I can draw that. It's just the x squared. It's shifted left by 2, so it should look like something like this. You know, again, not a great drawing, but it's the parabola that's shifted over there to the left by 2. All right. If I have, let's say, another function, let's say I have 1 over x minus 1. Right? So again, the parent function here, the governing equation, the parent function is 1 over x. I know what that looks like. It's essentially this guy, right? And so if I want to draw 1 over x minus 1, this is a shift to the right by 1 of 1 over x. And so my asymptote now is over here, which makes sense because if I plug in 1, I get 1 minus 1 in my denominator. I get 0 in the denominator. It's not defined there. So it's essentially just that equation, or that function, just drawn off to the right by 1. Again, I apologize. My drawing skills are not great on this thing yet, but that's what it looks like. All right. Now, we can have both transformations happening at the same time. So for example, let's look at the square root of x minus 2 plus 3. Right? It's important to note here that the plus 3 is on the outside of the function itself. So this is a shift up by 3. And inside here, this is a shift to the right by 2. So it's a square root function that I've shifted to the right by 2 and up by 3. That's easy enough. So without actually having to calculate points and see where this thing is, I just take my square root function, go right 2, up 3. That means I'm starting here. I know what the square root function looks like. It goes up 1 as it goes over 1, and then it just kind of does that and slows down in the increase as the x goes on, right? And that's it. That's the graph of this equation. Let's look at the graph of the absolute value of x minus 3 minus 4, right? So again, I know what the absolute value looks like. That's the v-looking function, right? Maybe I should make these bigger. I don't know. Will that help? I guess we'll find out. And straight. So I know what the absolute value is, but here I'm shifting this to the in the down direction by 4 and right. Remember that inside the function means left or right, but opposite the sign. So right by 3. So right 3 and down 4 means that the bottom of my V starts here. So all I have to do is pray to God that I can draw a straight line, and I can't. But close. And then go on the other side here. From here, up there, there. Wow, not very straight. I should probably just start using my ruler, but I'm not going to because it takes forever. But that's it. That's my graph of that function. Okay. Now, let's talk about reflection. So the reflection of a graph about the x-axis, there's no way in hell I'm drawing this because, I mean, I can't draw a straight line to save my life. So here's a picture of what that looks like. There's one. The black is the original function, and then the red is it being reflected about the x-axis. Here's another one. I'm just stealing these out of your book because they're right there, prime for me to steal them. Oh, what is that? Back up. I hate that picture so much. It's not what I wanted. So reflection of the graph about the x-axis, you'll notice that the only difference between the black graph, which is 1/5 x to the 4th, and the red graph, which is negative 1/5 x to the 4th, is that negative, right? So if I have some function, f of x, and I just negate the whole thing, that flips everything about the x-axis. Right? So negative f of x is the reflection of the function f of x about the x-axis. So if you have, let's say, some function of x, let's call it the negative square root of x, right? Well, that negative just means you're going to take the square root of x and flip it about the x-axis. So if I want to draw this, that's not helpful. I want this picture back. Copy. If I want to draw this, again, all I have to do is know that I'm reflecting this about the x-axis. I know what the square root of x looks like. It starts at 0. The reflection about the x-axis, if you're at 0, is still 0. But instead of going up now, it just gets reflected. Boy, it's so hard. That's not a great picture. That's much better. Well, it was. All right, but that's it. Instead of the original, which was up in this direction, ooh, that's worse. It just gets flipped down to the bottom, right? If you want to reflect about the y-axis, f of negative x is a reflection. Oh, I don't know why I'm writing this. I'm just going to do this. Of the function f of x about the y-axis. Right? So what am I talking about here? Well, if I have f of x is equal to the square root of negative x, right? Now all of a sudden x can't be positive, because if it is positive, that negative makes it a negative under the square root, so it flips, and the only ones I can use are negative x values, because the negative negates the negative, turns it positive, and so that does indeed flip it about the y-axis, and it looks like then that, right? I don't know why these are so hard. That's worse. But it looks like ish that, right? So if I have something like, say, just a random graph, let's say that it's f of x is red, and that, let's call it that. Then if I want to, I come in here and say, what is f of negative x? If I replace all of my x's with a negative and see what happens here, then it flips it. So it's going to look, I don't know why I did this to myself again. It's going to look like that-ish, right? It's just going to take that red and flip it all about that y-axis, and so I've created the blue. Okay. All right. All right, the next thing in here is stretching and shrinking. So where's my pen? There it is. C multiplied by the function. So whatever C is, if I have some value that gets multiplied by some f of x, this is the vertical stretch of f of x if c is greater than 1, right? If c is 1, then this is just f of x, and there is nothing happening. If it's greater than 1, it's going to take your function and stretch it, make it elongated in the vertical direction, right? But if c is less than 1, somewhere between 0 and 1, then it actually squishes it, right? So I'm going to say that this is the vertical compression of f of x. If 0 to 1, if x is somewhere between 0 and 1. We don't worry about the negatives because we just talked about negatives. If it's negative, it's a flip and then either a stretch or a compression, depending on if c is of magnitude greater than 1 or not, right? So let's take a look at a couple of examples here. I have some function. Let's say it is, let's say it's, I don't know, x to the 6. And then let's plop it 5 in front of it, right? So x to the 6, oh, I don't know what I'm doing. Yoke. So x to the 6 is going to have kind of a wide base. It still goes through the 0.11 and -11, right? But it kind of widens its base right here and then shoots up really quick. Because if you think about 2 to the 6, that's 2, 4, 8, 16, 32, 64. So by the time we hit 2, we're way off the screen. But it does something like this, shoots up real quick. So that, let's say, is 5x to the 6th. Oh, sorry, this is x to the 6th. Let me back up and make this not red. I'm going to make it blue. Because what I've just done in red is x to the 6th. Right? But if I want to graph 5x to the 6th, each one of these values gets multiplied by 5. So if it was 1 to start with, now it's 5. So both of these guys are 5. By the time you get to 2, 2 to the 6 was 2, 4, 8, 16, 30, it was 64. Now we're times 5, so we're 300, so we're way up there. So it's this huge stretch. And so all of these values get multiplied by 5, and it just rockets super fast up. And that is my stretch. That's not a great graph. Let's look at this one. Square root's nice because, I mean, I don't know, you can play with it a lot. So let's say I've got 3 root x. If I want to graph that, once again, I know what the square root of x looks like. It looks like this. So let's say my original square root of x looks like this. But if I'm multiplying everything by 3, then to graph this, instead of being at 1 here, I'm at 3. Instead of being, by here I get to, when I'm x is 4, I get to 2, because the square root of 4 is 2. But I have to multiply that by 3, so I'm like way up here at 12. Way up there, right? And so this thing then gets really stretched out. It's still going to follow that same pattern, but it just gets kind of, you know, humongously stretched out in the y direction, right? So if I zoom out of this thing, I'm still going to have that same general look to this thing. As I get higher and higher, it's going to chill out a little bit and go that way. But it's stretched a lot in the y direction, and so it kind of looks like that. Okay. Let's look at a compression. Oops, that's not helpful. Yoink. These are easier to see. Let's say that I have f of x equals 1/8 x squared. Right? So I know what x squared looks like. It's this parabola that goes through 1 and then 2, 4, and then up. Goes through -1, 1, -2, 4, and then up. Again, I apologize, my graphing is terrible, but I'm just going to quit saying it because we all know by now. But if I want to graph 1/8 x squared, then everything is compressed by a factor of 1/8. And so instead of being at 1 right here, I'm now at 1/8. Instead of being at 4, I'm at 1/8 of 4, which is 1/2. And so I can see that this thing really flattens out and gets pushed down. It's still a parabolic arc, and it goes like this, but it's really been squished, right? It's been taken and squished down so that all of the y values are 1/8 of what they started. All right. That is vertical stretching and compressing, or shrinking. They also call it shrinking. I like to say it as compressing because that's how I view it. But for horizontal compression, f of c times x. So now the c is inside the function. Everywhere there's an x, if it's multiplied by c, this is the horizontal stretch if c is greater than 1, or if it's less than -1, right? If it's further away from 0 than 1. But if it's negative, it's going to be that horizontal flip first, and then if the magnitude is greater than 1, then it's a stretch, right? But if c is greater than 1, it's a stretch. But is the horizontal compression if it's somewhere between 0 and 1, right? So what I mean by this is if I have f of x equals, say, the square root of 2x, right? Oh, I wrote these wrong. I erase that. No, I cannot. But what I can do is this. These are opposite. Whenever you stick stuff inside the parentheses, opposites tend to happen. It is a compression if c is greater than 1 and a stretch if c is between 0 and 1, right? Okay. And I'll show you why that is. But with this f of x, let's say, is 2x. C is 2, which fits this category here. It's greater than 1, so I have a compression of 1/2, right? It's 1 over c. So that looks like this. Obviously, like, let's just throw in some values here and we can kind of build this. But f of 0 is, well, 2 times 0 is 0 and the square root of 0 is 0. So let's say that we have the f of 2, because that is 2 times 2 under a square root, but that's 2 squared is 4, or the square root of 4 is 2, right? And I think just those 2 points are sufficient because that gives me 0, 0. But it also gives me the point when x was 2, my y value was 2, so I'm right there, right? And so I end up with a square root function that looks like this. I missed. But the normal, if I'm looking at f of x being the square root of x, then I have f of 4 is the square root of 4, which is 2. So normally this point that I drew is not until here, which is to say I've been compressed by 1/2, right? The function at 1 of just the square root is just 1, so this guy that was at 1 is now at 1/2. So all of these values got squished in by a factor of 1/2, right? As opposed to if I wanted to draw f of x equals, let's say, the square root of 1/2 x. Now this is a compression by a factor of 2, right? 1 over that c value, 1 over 1/2, which is 2. So if I draw this guy, everything gets squished, or not squished, but pushed to the right by a factor of 2. So instead of being at 4, I'm going to be off all the way down here at 8. And so it really kind of pushes this guy in a horizontal stretch, right? Pulls everything off to the side. Okay. And that's it for section 2.5. So let's look at 2.6. Clear this off here. And 2.6 is called variation and application. So the first thing we would have is called direct variation. And you might see this as y, something like y varies directly with x, or varies directly as x varies, or something to that effect, right? The idea here is, you know, say John earns $20 an hour, right? This describes a direct variation between John's earnings, which we'll just call E, perhaps, for John's earnings, how much he earns. And this is $20 for every hour he works, where X is, in fact, you can use H, whatever, it doesn't matter, 20 H. That's a direct variation. As H goes up, every 1 unit H goes up, E, his earnings, goes up by $20, right? So this is a direct variation. A lot of times you'll see it as simply y equals k times x, where k is some constant for that problem. In this problem that we had, k was 20, right? So a lot of times you might have to actually figure out what k is, but it's going to be the same value through that problem. When you go to a different problem, it's probably going to be a different k, a different value, but you can consider it constant for the problem you're working on, right? So sometimes we have to figure out what k is before we can answer the question that they ask us. So let's say we have this. Y varies directly with x. And let's say if y is 20 when x is 5, find y when x is 4. So it's a direct variation, so I know that I'm using this formula. I know it's going to be y equals k times x, right? And I'm given a scenario here. Y is 20 when x is 5. So I can plug in those values. Y is 20. That equals k times x. X is 5. And I can solve for k. All I have to do is divide each side by 5. 20 divided by 5 is 4. So I know that k is 4, right? Okay. And then the other scenario here says, well, find y when x is 4. Well, I know that k is 4, so I know that my equation is going to be y equals 4x. But if x is 4, then y is then 4 times 4 and is then 16 for that value, right? Let me grab this one real quick here. I'm going to steal this from the book. There we go. All right, so here's a problem in the book, water for melting snow. Excuse me just one moment. Okay. All right, sorry about that. The number of centimeters, W, of water produced from melting snow varies directly as S, the number of centimeters of snow. Meteorologists have found that under certain conditions, 150 centimeters of snow will melt to 16.8 centimeters of water. So let's look at this and say, from this first equation, the number of centimeters, which we're calling W, of water produced from melting snow varies directly as S. So let's say water is a constant is an S out of 5. S. That's better, isn't it? So that's our equation. And then they say the number of, let's see, meteorologists have found that under certain conditions, 100 centimeters of snow, which is my S value, will melt to 16.8 centimeters of water, my W value. So I can plug that in. 16.8 centimeters of water came from K multiplied by snow, which was 150 centimeters. So if I divide each side by by 150, I get, I'm just going to cheat because I have it in front of me somewhere, 0.112 is K, right? So I know then that the formula that I'm going to use is W equals 0.112 S, right? And I can then go on to the next little bit. How many centimeters of water? So I'm looking for water, but I know that K is 0.112. How much water will 200 centimeters of snow? So I just plug in 200 into that, and I multiply the two, and this gives me 22.4 centimeters of water. And that's our direct variation. The other type here in this section is called inverse variation. The inverse variation is things like, what's an example of an inverse variant? I mean, there's physics stuff like gravity. I mean, that's a bad one because that's inverse square. So forget that. Let me see. Oh, there's an example here. We'll go through an example, but the inverse variation essentially says that if y varies inversely, with x or as x or whatever, then we have the equation y equals still that k, that constant of proportionality, but now it's divided by x, right? That's the inverse, is to have x in the denominator. So if y varies, I like how I spelled varies, don't judge me. It's like 1130, I guess not. Anyway, if y varies inversely with x, then we've got this function, right? So if, and you might see a question like this, if y varies inversely with x, and y is 8 when x is 30, find y when x is, I don't know, What do I want? I don't know, 20. Doesn't matter. So again, because y varies inversely with x, I have that function. I know I'm dealing with y equals some k divided by x. But I know that y is 8 when x is 30, so I'm going to plug these values in. So 8 equals k divided by 30. I can solve for k by multiplying both sides by 30. So that cancels and leaves me with k on the right-hand side. 8 times 30 is 240. And so that's my k. And so for the next part, find y when x is 20. Well, y is, I know k is 240 divided by x, which we're saying is now 20. And so then I get y is 12. Okay. All right. Here's an example of this. And there's a lot of examples. I just can't think of one that would make a whole lot of sense. But this one's pretty, I mean, it's all right. It'll do. The time required to fill a swimming pool varies inversely as the rate of flow of water into the pool. A tank truck can fill a pool in 90 minutes at a rate of 1,500 liters per minute. How long would it take to fill the pool at a rate of 1,800 liters per minute? So the first thing that we want to note here is that the time to fill a swimming pool varies inversely as the rate, right? So that is to say, time varies inversely with rate. I can have t equal time, r is rate, and then my inverse relationship here is that t equals k over r, where k is that constant of proportionality. If a tank truck can fill a pool in 90 minutes, so the amount of time in this scenario is 90 minutes at this rate, that tells me that I have 90 equals this k over that r is 1,500. Right? So then I just simply multiply both sides by 1,500. Cancels it out and leaves me with a k on the right-hand side. But I'll multiply it by 1,500 over here. And that leaves me with 135,000. So that's my k. Then the question is, how long, so I'm looking for the time, would it take to fill the pool at a rate of 1,800 liters per minute? So I'm looking for t. T is k over x, but k I know is 135,000. But now I'm dividing it by 1,800, right? So that's it. I just plop that into a calculator. Excuse me. Calculator. And this is 75 minutes. Excuse me. Yeah, so that is our inverse variation. Now, they might get a little bit tricky on you, and they might do something like this. I don't know, 10. Right? So we've got this. Y varies inversely, so that should tell us that we've got that y equals k over. But it's not with x anymore, it's the square of x. So it's a little tricky. They snuck the square in there, but, and by they, I mean I just wrote this, but this means that I have y equals k over, not just x anymore, but it's x squared, right? Because it's inversely with the square of x, not just x. So I can still go through this process. If y is 2 and x is 4, y is 2 when x is 4. This is to say that 2 is equal to k over 16. So I multiply both sides by 16. So k is 32. And I want to find y when x is 10. So y equals that k, which was 32, over 10 squared, right? Don't forget that your initial function has a square in the denominator. So it's 32 over 10 squared. That is 32 over 100, or 0.32. All right. And then let's look at another one here. Y varies directly jointly with x and z. Right? So if you see something where it varies directly jointly with x and z, this means that your equation is going to be y equals k times x times z. Right? And so if I have this one, and let's say that y is 120 when x is 8 and z is, let's say, 5, right? And we want to find y when x is 2 and z is, let's say, 6. Okay? So it's this equation, y equals x times k times z. The y is 120 when x is 8 and z is 5. So 8 times 5 is 40, so I get 120 is 140k. I'm going to write it 140. I'm going to write it this way with the 40 in front, just because that's habit. And then if I divide each side by 40, I can solve for k. And so I get k is 3. Now, the next part of it says find y when x is 2 and z is 6. So y equals k, which is 3, multiplied by x, which is 2, multiplied by z, which is 6. And I just multiply this all together, and I end up with 36. Okay. And of course, they can do all sorts of funky junk with their language. Let me snag example 7 here, because it is indeed funky. Oops. All right. Find an equation of variation in which y varies jointly as x and z and inversely as the square of w and y equals 105 when x equals 3, z equals 20, and w equals 2. So there's a lot going on here. So I'm going to just cut this sentence off right here at the end. We'll get to that in a minute. We want to find an equation of variation in which y varies jointly as x and z, and inversely as the square of w. So I have that, right? This varies jointly with x and z and inversely with the square of w. So that's my function, right? I can figure out k by this information. Y is 105 when x is 3, z is 20, and w is 2. So that is 2 squared. So I can simplify a bit. I've got 105 still on the left. On the right, 3 times 20. I'm going to write that as 60k. That 0 kind of ran away from the 6 there. 60k all over 2 squared is 4. So again, I can simplify the 60 and 4. I'm going to take this right up here. 105 is equal to 60 divided by 4 is 15, so I have 15k, right? And then, of course, I can solve this by dividing each side by 15. And so divide this by 15, divide this by 15. The 15s cancel out. This ends up being 7, and it's that. Now, they don't ask you the follow-up question, find y when x equals this, y equals that. They just wanted the equation. So the equation is this that we started with, but I know k is 7, right? So my final answer is y equals 7xz over w squared. That's the equation they're looking for. We'll see stuff like this in physics. Gravity is like this. I mean, there's lens not so much lens equations, but there's all sorts of inverse squares and direct variation, things like that. So anyway, that's it. That's 2.6. Again, if you have questions, I'm available to answer those for the last 30 minutes or so of class or during office hours. So if you can't make it during those 2 times, email me and we can, I'll answer questions. So thanks, and I will see you guys next time.